Have you ever really stopped to think about that invisible force that powers pretty much everything in your life? Well, today, we're going to trace the incredible journey of electricity, all the way from a massive power station through miles and miles of wire right into that socket in your wall. So let's get plugged in.
Okay, to kick things off, here's a question for you. We all kind of know you can't just power your TV with a bunch of AA batteries, right? But why exactly? What's the fundamental reason? Well, it all comes down to the fact that electric current has two very different personalities.
And yep, those two personalities are AC and DC. That's alternating current and direct current. Understanding this one key difference is really the first big step to figuring out the power that's flowing all through your home.
So on one side, you've got direct current, or DC. Just think of it like a calm, steady river, flowing smoothly in only one direction. But on the other side, you've got alternating current, AC, which is way more like a powerful tide that's constantly, and I mean rapidly, reversing its flow back and forth.
Direct current, or DC, is really the power of portability. It's what you get from batteries, in your phone, your laptop, even your car, and you also get it from solar panels. It's just a reliable, unwavering flow, always pushing in one direction. If you were to draw its voltage on a graph, it'd just be a perfectly straight, flat line.
And then there's AC, the absolute powerhouse of our modern world. Now you might be thinking, why have this complicated back and forth system? Well, it's because AC voltage can be changed really easily with transformers. That makes it incredibly efficient for sending power over huge distances from the power station to your town. This is actually why AC famously won the war of the currents against DC way back in the day.
All right, so now we know our homes run on AC. Let's zoom in a little closer and look at the specific kind of electricity that's coming out of a socket here in the UK. Its whole personality is basically defined by just two crucial numbers.
The first number is 230 volts. Now, the best way to think of voltage, or potential difference, is as the pressure in the electrical system. It's the force, the push, that shoves the current through the wires and into your gadgets, giving them the energy they need to work.
And the second really important number is 50 hertz. So if voltage is the push, then frequency, which we measure in hertz, tells us all about the rhythm of that push.
So what does 50 hertz actually mean? It means the current in your walls is flipping its direction back and forth 50 times every single second. That speed is just incredible. And as a little fun fact, over in North America, they use a 60 hertz system. It's just a fascinating difference in engineering standards around the world.
Okay, so how do we safely tap into this powerful, super fast oscillating current? Well, that's where this very familiar piece of engineering comes in, the 3-pin plug. It's so much more than just a simple connector. It's a vital gateway and a little miniature safety system all rolled into one.
But before we even get to the plug, let's look at the cable it's attached to. It's such a simple but brilliant partnership. At its core, you've got copper, which is an amazing conductor. It basically gives electricity an easy superhighway to travel down. And then wrapped around that highway is a thick layer of plastic, a fantastic insulator, whose whole job is to keep all that powerful electrical energy safely contained inside.
Now, inside that plastic coating, you'll find a team of 3 wires, and each one has a critical job to do. First up, the brown wire. That's the live wire, and it carries the full 230 volts of electrical pressure. Then you have the blue wire, the neutral. It sits at almost 0 volts, and its job is to complete the circuit, giving the electricity a path to return. And finally, the green and yellow striped wire. That's the earth wire. Most of the time, it does absolutely nothing, but it's arguably the most important one, because it's a critical failsafe for when things go wrong.
So we get how electricity is delivered, but what about how much energy our appliances actually use? Why does a kettle boil water so much faster than a tiny little nightlight can light up a room? It all comes down to a concept called power, which we measure in watts.
To put it simply, power is just about how quickly an appliance uses energy. It's a measure of an appliance's thirst for electricity. A really powerful 2,000-watt hairdryer is just guzzling energy way more rapidly than, say, a 10-watt phone charger. And that's why its effect is so much more dramatic. And the great thing is, there's a beautifully simple little formula to figure all this out. Power is just the potential difference. That's our voltage, the electrical push, multiplied by the current, which is the flow of electricity. So power equals volts times amps. P equals V times I. With this little equation, you can unlock the energy secrets of pretty much any device in your house. Let's try it out with a real-world example. Imagine you have a pretty powerful electric heater.
We know the UK main supply gives us 230 volts, and let's say that heater draws a current of 12.5 amps. So what's its power rating?
Well, we just multiply those two numbers together. 230 volts times 12.5 amps gives us 2,875 watts. That is a pretty power-hungry appliance.
Okay, for our final section, let's look at the really clever safety features that are built right into our electrical system. I mean, having 230 volts on tap is incredibly useful, but it definitely demands respect. Luckily for us, our plugs and wiring have some ingenious features that are designed to be our silent bodyguards.
Let's imagine a dangerous but totally possible scenario. Picture a fault inside an appliance with a metal case, something like a toaster or a kettle. The live wire comes loose and it touches the metal casing. All of a sudden, that entire metal surface is live at 230 volts. So what stops you from getting in deadly shock the moment you touch it?
This is where that safety system kicks in with lightning speed. Remember that green and yellow earth wire? The second that casing becomes live, that wire provides a super easy, low-resistance path for all that current to surge away safely into the ground. This creates a massive spike in current, way higher than normal, and that spike is the trigger for the final step.
That massive surge of current flows straight through a tiny device in the plug called a fuse. Now, a fuse is basically a purpose-built weak link. That huge surge of current is far too much for the thin little wire inside the fuse to handle. It instantly overheats, melts, and breaks the circuit completely, cutting off all the power. And this all happens in just a fraction of a second.
This tiny, really inexpensive little component is just a masterpiece of safety engineering. Think about it. It's a deliberate point of failure. It's a tiny wire that is designed to fail so that something much more important, the appliance, and most of all you, doesn't have to. It's just a fantastic example of the hidden ingenuity that's working all around us, keeping us safe every single day.